In March 1995 in Indianapolis, General Motors did something unthinkable. It sold off the Allison Engine Company to a British rival, Rolls-Royce, for $525 million. For 66 years, Allison had been GM's aerospace crown jewel. This was the factory that built over 70,000 liquid-cooled V-1710 V12 engines for World War II fighters like the P-38 Lightning. This was the plant that engineered the T-56 turboprop, the relentless mechanical scream behind the C-130 Hercules. But facing a crippling corporate financial crisis, GM severed its ties to the sky. Thousands of American aerospace workers suddenly answered to London. Yet the most bizarre part of the sale was what General Motors decided to keep. They sold the aviation engine division, but they kept the commercial transmission business, and they kept the Allison name for the American highway. But the real story of Allison is not only the story of a 1995 corporate buyout. It is the story of how an American engine empire moved from piston thunder to turbine scale, and how a name built for the sky survived as a badge of heavy-duty trust on the ground. Every week, we tell the stories of American engines, factories, machines, and industrial names that once taught the country what power sounded like and what happened when the market moved on. Subscribe if that history matters to you. The story of Allison begins not with nostalgia, but with a specific precision machine shop in Indianapolis, Indiana in 1915. The story begins in Indianapolis, Indiana in 1915. At the time, James A. Allison was not trying to conquer the sky. He was trying to survive the racetrack. Allison was one of the original founders of the Indianapolis Motor Speedway. In the early days of American auto racing, the machines tearing across the brick oval were brutal, experimental, and incredibly fragile. Engines were blowing apart under the stress of sustained high-speed runs. Mechanics were struggling to find replacement parts that could withstand the heat, vibration, and violence of the track. Allison realized that the problem was not just the design of the cars, it was the metallurgy and the machining. To solve this, he opened a precision machine shop on Main Street and Speedway, right near the track. He called it the Indianapolis Speedway Team Company. He hired a small crew of elite machinists and engineers, and they began building custom parts, superchargers, and gears. They did not build machines for the masses. They built machines for people pushing metal to its breaking point. The American absence at the time was clear. American manufacturing was already brilliant at mass production. Henry Ford had proven that in Detroit. But mass production relied on standard tolerances, good enough for a farm truck or a city runabout. What America lacked was a scaled system for extreme precision, parts machined to the thousandth of an inch, capable of surviving environments where a single flawed bearing meant catastrophic failure. When the United States entered World War I in 1917, the military realized they needed exactly that kind of precision. The government was rushing to produce the Liberty L-12, an aircraft engine designed to power the American war effort. But the Liberty was complex, and standard automotive factories struggled to build the delicate, high-stress components it required. Allison's shop was handed contracts to build reduction gears, supercharger parts, and heavily stressed bearings. The racing shop had been pulled into the aviation supply chain. Following the war, the company was renamed the Allison Engineering Company. They spent the 1920s surviving on specialized contracts, modifying Liberty engines, building marine engines, and refining the art of the supercharger, a mechanically driven device that forces more air into the engine, allowing it to produce power at higher altitudes where the air is thin. They remained small, employing fewer than 200 men. They were a boutique operation, highly respected by the military, but largely unknown to the American public. Then in 1928, James Allison died. The following year in 1929, the small Indianapolis firm caught the attention of a corporate giant. General Motors bought the Allison Engineering Company. At first glance, it was an odd acquisition. GM was an automotive empire, heavily invested in cast iron, assembly lines, and consumer cars. Allison was a low-volume laboratory of perfectionists, but General Motors wanted a foothold in the growing aerospace industry, and they saw Allison's precision machining culture as an asset they could not easily replicate in Detroit. This corporate backing arrived at the exact moment the United States military was facing a quiet crisis in the sky. Throughout the late 1920s and early 1930s, the American aviation industry was completely obsessed with the radial engine. A radial engine, a piston aircraft engine with cylinders arranged in a circle around the crankshaft, was rugged, air-cooled, and reliable. Because it used the passing wind to cool its cylinders, it did not need heavy radiators, water pumps, or vulnerable coolant hoses. Companies like Pratt & Whitney and Wright Aeronautical were building radial engines that dominated American bombers and transport planes. But the radial engine had a physical flaw: its shape. A circle of cylinders creates a massive, blunt nose on an airplane. In the early 1930s, military observers watching the European powers noticed something alarming. Companies like Rolls-Royce in Britain and Daimler-Benz in Germany were pouring money into liquid-cooled engines. A liquid-cooled engine, an engine that pumps a coolant mixture through channels in the engine block to carry heat to a radiator, could be built in a long, narrow V-shape. This allowed an aircraft designer to wrap the fuselage tightly around the engine, creating a streamlined aerodynamic nose that could slice through the air at much higher speeds. The United States Army Air Corps realized they were falling behind. They needed a high-horsepower, liquid-cooled engine to power a new generation of fast, sleek interceptor fighters. And they turned to the newly GM-backed Allison Division in Indianapolis to build it. Under the direction of engineer Norman Gilman, Allison began working on a massive 12-cylinder engine. The target was 1,000 horsepower. The displacement, the total volume swept by the pistons inside the cylinders, was a staggering 1,710 cubic inches. To put that into perspective, a large American V8 in a heavy-duty pickup truck today might displace around 400 cubic inches. The Allison engine was more than 4 times that size, packed into a block designed to be as light and rigid as possible. It was officially designated the V-1710. The development of the V-1710 through the 1930s was an agonizing process of trial, error, and mechanical violence. The engine, a machine that turns fuel into mechanical motion, was constantly tearing itself apart on the test stands. Cylinder heads cracked, crankshafts, the rotating shafts that turned piston motion into rotational power, snapped under the immense torsional stress. Valves burned out. The Great Depression severely limited government funding, meaning Allison and General Motors had to finance much of the painful development process themselves. For years, the V-1710 was a laboratory experiment, a temperamental beast confined to a test cell in Indiana. The mechanics and engineers at Allison had to invent new casting techniques, new bearing materials, and new machining protocols just to keep the engine together at high RPMs. They were no longer just a machine shop. They were becoming a metallurgical research facility. The breakthrough finally came in 1937. The Army required any new aircraft engine to pass a brutal 150-hour endurance test, running at maximum power, before it could be certified for combat aircraft. For years, liquid-cooled engines in America had failed this test. But that spring, inside a heavily reinforced test cell in Indianapolis, the Allison V-1710 roared for 150 hours straight without a catastrophic failure. It became the first engine in American history to officially pass the 1,000 horsepower certification mark. The blueprint was ready, but it would take a global war to prove whether a Midwestern machine shop could build the engines that would control the sky. When World War II erupted in Europe in 1939, the United States military was caught in a dangerous position. The American aviation industry was dominated by massive air-cooled radial engines. While these were incredibly durable and perfect for heavy bombers and transport planes, their wide, flat faces created massive aerodynamic drag. The military desperately needed sleek, high-speed interceptors, and there was only one engine in America ready to fit that aerodynamic profile: the Allison V-1710. Overnight, the fate of American fighter aviation rested on a single factory in Indianapolis. General Motors, realizing the immense scale of the impending conflict, poured capital into Allison. They built Plant 3, a massive, windowless, blackout-ready manufacturing facility. The workforce, which had hovered around a few hundred men just years earlier, exploded. Thousands of workers, including a massive influx of women, were brought in to run the lathes, operate the casting foundries, and inspect the precision bearings. The transition from a boutique machine shop to a wartime industrial giant created immense tension. The V-1710 was not a cast-iron Chevrolet block that could be slapped together with loose tolerances. It was a high-strung aviation power plant that required clearances measured in 10,000ths of an inch. A single flaw in a connecting rod, the steel arm that links the piston to the crankshaft, meant an engine would disintegrate in combat. General Motors had to teach an army of new factory workers how to mass-produce a machine that had the complexity of a mechanical watch, but the explosive force of a locomotive. To understand the breakthrough, you have to understand the fundamental difference in how these machines managed heat. A liquid-cooled engine, an engine that circulates a chemical coolant mixture through passages in the metal block to absorb heat, then sheds that heat through a radiator exposed to the airstream, changes the entire system of an airplane. On an American military runway in 1941, an aircraft mechanic assigned to an Allison-powered fighter was no longer just managing oil, spark plugs, and valves. They were managing plumbing. A liquid-cooled engine meant coolant pumps, heavy rubber hoses, vulnerable radiators, and the constant threat of leaks. If an enemy bullet punctured the radiator of a radial engine, it would keep flying until the oil ran out. If a bullet punctured the coolant system of an Allison V1710, the engine would overheat, seize up, and turn into a dead weight of molten metal in a matter of minutes. But the aerodynamic trade-off was entirely worth the risk. The V1710 allowed aircraft designers to build airplanes shaped like bullets. The first major beneficiary was the Curtiss P-40 Warhawk. The P-40 was a rugged, heavily armored fighter that became famous in the hands of the American Volunteer Group in China, better known as the Flying Tigers. The Allison engine in the P-40 was not equipped with a two-stage supercharger, a complex mechanical air compressor that rams high-density air into the cylinders to compensate for the thin atmosphere at extreme altitudes. Because of this, the P-40 struggled in high-altitude dogfights against German and Japanese interceptors. But down low, in the thick air under 15,000 feet, the Allison V1710 gave the P-40 brutal acceleration and the power to become a legendary low-level brawler and ground attack aircraft. Then came the Lockheed P-38 Lightning. The Lightning was a radical twin-boom fighter that used two Allison V1710 engines. To solve the high-altitude problem, Lockheed equipped the engines with turbochargers, devices driven by the hot, expanding exhaust gases that force massive amounts of compressed air into the engine. A turbocharged Allison V1710 was a vastly different machine. It gave the P-38 Lightning the ability to climb into the freezing, thin air above 30,000 feet and dominate the Pacific theater. In an American hangar during the war, the sound of two turbocharged Allisons sinking their idol was the mechanical signature of a heavy fighter that had the range to cross vast oceans and the speed to catch anything in the sky. The Allison engine was also the original heartbeat of the North American P-51 Mustang. The early P-51A models were designed specifically around the shape of the V1710. The result was an incredibly fast, aerodynamic masterpiece that dominated the low altitudes. While later models of the Mustang would switch to the British-designed, Packard-built Rolls-Royce Merlin engine to achieve better high-altitude bomber escort performance, it was the Allison block that proved the Mustang's airframe was a lethal weapon. Through all of this, the Indianapolis factory roared 24 hours a day. The machine lines were soaked in cutting fluid. The test cells, heavily reinforced with thick concrete, vibrated non-stop as newly assembled V-12 engines were run up to full power to ensure they would not fail over the Pacific Ocean or the English Channel. General Motors had successfully taken a delicate, temperamental prototype and turned it into an industrial commodity. The scale of this achievement was staggering. By the time World War II ended in 1945, the Allison division had manufactured over 70,000 V1710 engines. The name Allison was no longer associated with a small racing shop. It was recognized by every pilot, mechanic, and aviation enthusiast in the United States as a pillar of American industrial might. The V1710 had proven what the Indianapolis factory could do with pistons, but the sound of American power was already changing from a mechanical roar to a high-pitched scream. When the V1710 production lines finally halted after the Allied victory in 1945, the American aviation industry faced a brutal contraction. The massive air-cooled radial engines that had powered heavy bombers were suddenly reaching the physical limits of piston technology. Companies like Wright Aeronautical, which had dominated the sky for decades, found themselves fatally wounded by their inability to transition quickly to the new era of propulsion. Allison could have easily become a casualty of this post-war collapse. But Allison had a unique advantage. It was wholly owned by General Motors. GM possessed the vast industrial capital required to tear out the piston machinery and completely retool the Indianapolis factories for a terrifying new technology. The sound of American aviation was changing from a mechanical rumble to a high-pitched scream. The United States military was moving into the jet age. To bridge the gap, the government brokered a massive industrial handover. General Electric had developed early jet engine prototypes, but they lacked the sheer manufacturing floor space and mass production experience to build them at a wartime scale. General Motors stepped in, and the Allison division was handed the responsibility of mass-producing the J-33 turbojet. A turbojet, an engine that produces thrust entirely by pulling in air, compressing it, mixing it with fuel, and accelerating a continuous stream of ignited exhaust gas out the back, was an entirely different metallurgical discipline. The machinists in Indianapolis had spent a decade mastering the tight clearances of connecting rods and crankshafts. Now they had to learn how to cast and machine turbine blades, delicate fin-like metal components that had to survive inside a literal firestorm of continuous combustion without melting or stretching under immense centrifugal force. They succeeded. Allison built over 15,000 J-33 engines, powering early jet fighters like the Lockheed P-80 Shooting Star. But the true glory of the Allison engine empire, the machine that would grant them absolute scale and dominance throughout the Cold War, was not a pure turbojet. It was a hybrid of turbine heat and mechanical torque. It was the Allison T56 turboprop. A turboprop, a turbine engine that uses its high-speed gas flow not just to create thrust out the exhaust, but to spin a series of turbine stages attached to a heavy reduction gearbox, which in turn drives a massive external propeller, solved a critical problem for the American military. Early pure jets were incredibly fast, but they consumed fuel at an alarming rate and required long, perfectly paved runways to get heavily loaded transport planes off the ground. The United States Air Force needed a tactical airlifter that could carry tanks, troops, and artillery, fly across oceans with extreme fuel efficiency, and land on short, unpaved dirt strips in the middle of nowhere. To do that, an aircraft needed the massive, instantaneous pulling power of a propeller, combined with the lightweight, high-horsepower output of a turbine. In 1954, Lockheed introduced the C-130 Hercules, a blunt, four-engine military transport plane that would become the most successful military airlifter in global history. The heartbeat of the Hercules was 4 Allison T56 turboprop engines. The scale of this operation transformed Indianapolis. The T56 was not a limited-run experiment. It was a permanent industrial contract. Plant 8 in Indianapolis became a sprawling aerospace complex dedicated to turbine power. The Allison badge was now synonymous with the unrelenting, synchronized drone of 4 turboprops carrying American logistics across the globe. In an America where an engine could decide whether a field was cut, a truck made its delivery, a boat left the dock, a generator carried a hospital through a storm, or a plane lifted from the runway, power was not an abstraction. It was iron, fuel, labor, heat, sound, repair, and trust. For the mechanics and flight crews operating on remote dirt airstrips from Southeast Asia to the Arctic Circle, the Allison T56 was the absolute embodiment of that trust. The engine was famously durable, capable of swallowing dust, operating in freezing rain, and running on almost any combustible aviation fuel. It was a masterpiece of American engineering, and it firmly cemented Allison as General Motors' most prestigious division, a cash-generating aerospace giant hidden inside a car company. Over the coming decades, Allison would produce more than 18,000 T56 engines. The empire had reached its absolute peak, and the Indianapolis assembly lines were running around the clock to supply the military. But the foundation of that empire was tied to a corporate balance sheet in Detroit, and that balance sheet was hiding a fatal flaw. The military dominance of the T56 turboprop was absolute, but to become a true American engine empire, Allison had to conquer the commercial market. General Motors authorized the adaptation of the military turbine into a civilian variant known as the Allison 501D. By the late 1950s and into the 1960s, if an American business traveler was boarding a regional flight on a Lockheed L-188 Electra, they were flying on Allison power. Later, when regional airlines needed to upgrade their aging piston-powered Convair aircraft, they ripped out the old radial engines and bolted on Allison 501D turboprops, creating the Convair 580. The sound at regional American airports changed entirely. A constant speed turboprop does not rev up and down like a car. The engine runs at a continuous, ear-splitting 13,820 RPM, while the propeller blade angle changes to adjust thrust. That relentless, high-pitched turbine whine became the auditory signature of modern American efficiency. Back in Indianapolis, the manufacturing footprint required to sustain this empire was staggering. Plant 8 was no longer just a factory. It was a sprawling, self-contained industrial ecosystem. Thousands of American workers arrived for every shift. They were no longer just cutting steel. They were casting and machining exotic aerospace metallurgy. They were working with high-nickel alloys designed to survive inside a continuous firestorm, temperatures that would melt a standard Chevrolet cast-iron block into a puddle. This hardware required a massive, dedicated support system. A turbine engine is incredibly reliable, but it eventually requires an overhaul, a major service process where an engine is completely taken apart, inspected down to the microscopic wear on individual compressor blades, and rebuilt to strict aviation operating standards. Allison did not just sell engines. They built a global service network, from commercial maintenance hangars in Miami to freezing, windswept airstrips in Alaska. Mechanics relied on thick, oil-stained Allison service manuals, authorized parts distributors, and a logistical supply chain that ensured a grounded aircraft would not stay grounded for long. As the Cold War progressed, Allison expanded its turbine footprint even further into the low-altitude infrastructure of American life. They developed the Model 250, a lightweight turboshaft engine. A turboshaft, a turbine engine that delivers its power to a shaft to drive a helicopter rotor instead of an airplane propeller, changed the aviation market again. The Allison Model 250 became the most successful light helicopter engine in history, famously powering the Bell Jet Ranger. Suddenly, Allison was everywhere. If a local news station was broadcasting traffic over a Los Angeles freeway, they were hovering on Allison power. If a medevac helicopter was landing on a rural highway to save a life, it was relying on an Allison turbine. If an agricultural pilot was crop dusting a massive Midwestern farm field, they were listening to the steady scream of a Model 250. By the 1980s, the Allison division had become a financial fortress. The contrast with the rest of General Motors was striking. While Detroit was battling severe fuel economy regulations, emission standards, and a brutal invasion of foreign automotive imports, the aerospace division in Indianapolis was quietly generating massive, reliable profits. The continuous government contracts for the C-130 Hercules, combined with deep commercial market penetration, provided a steady stream of revenue that helped prop up the automaker's bottom line. The Allison badge had become a symbol of absolute mechanical trust. In an era where American industrial dominance was beginning to show deep structural cracks on the ground, the Indianapolis factories proved that the United States could still build the most reliable aerospace power on Earth. The workforce was proud, the supply lines were strong, and the engines were deeply embedded into the fabric of global logistics. Allison had mastered the sky, but it was still owned by a car company. And in the 1990s, General Motors was about to face a balance sheet that could not afford to keep flying. The first crack in the Allison empire did not happen on a runway, and it did not happen inside a test cell. It happened quietly in the late 1980s as global geopolitics began to shift. For decades, the sprawling Plant 8 in Indianapolis had been insulated from the economic turbulence of the standard American automotive market. They were building the T-56 turboprop for the C-130 Hercules and the Model 250 turboshaft for military and civilian helicopters. Their revenue was backed by the relentless, unquestioned budget of the Cold War. But when the Berlin Wall fell in 1989 and the Soviet Union collapsed shortly after, the United States government immediately began to slash defense spending. Almost overnight, the massive military contracts that had sustained the aerospace industry slowed down. Existing aircraft were kept in service longer, New fleet orders were delayed or canceled. The Indianapolis factories were still producing engines, but the backlog of guaranteed government work began to shrink. The mechanics and machinists on the floor, men and women who had spent their careers working with exotic aerospace alloys, started to see the pace of the assembly lines change. Yet the true threat to Allison was not a lack of engineering capability. The pressure came directly from the mechanics of corporate ownership. This was a classic case of corporate consolidation and brand survival. The engine could still run perfectly. The economics of the company that owned it were failing. By the early 1990s, General Motors was in a state of absolute financial crisis. The core automotive business in Detroit was bleeding cash. GM was losing market share to highly efficient, reliable Japanese imports. They were weighed down by aging, inefficient car factories, massive legacy labor costs, and a product line that struggled to adapt to changing consumer expectations. In 1992, General Motors reported staggering, historic, multi-billion-dollar losses. The boardroom in Detroit was forced into a brutal reorganization, looking to shed anything that was not directly related to saving their passenger cars and trucks. Allison was caught in a fatal corporate paradox. On paper, the Allison division was still generating revenue. They were a profitable aerospace company trapped inside a failing automaker. But the aerospace industry is not a static business. To stay relevant in the turbine engine market, a company must constantly pour billions of dollars into research and development. A new generation of jet engines requires advanced metallurgy, massive testing facilities, and years of zero-profit engineering before a single engine is ever sold. General Motors looked at their balance sheet and realized an inescapable truth. They could not afford to finance the next generation of American aircraft engines while simultaneously trying to save Chevrolet, Buick, and Pontiac. They simply did not have the capital to compete with dedicated aerospace giants like Pratt & Whitney or General Electric. The corporate parent could no longer afford its crown jewel. In 1992, GM executives made the decision to put the Allison gas turbine division up for sale. But separating Allison from General Motors was not as simple as signing a document. Over the decades, the Allison name in Indianapolis had grown to encompass more than just aircraft engines. While Plant 8 was building turbines, other parts of the Allison manufacturing complex had been building heavy-duty commercial transmissions. A transmission, the complex gearbox that takes the rotational power of an engine and multiplies it into usable torque for the wheels, had become another pillar of the Allison brand. They were building massive automatic transmissions for city buses, earth-moving equipment, military tanks, and highway trucks. The transmission division was deeply integrated into GM's commercial truck strategy. So, in late 1992 and early 1993, General Motors brought down a corporate knife right through the center of Indianapolis. They cleaved the historic company in half. The aerospace division, the engineers, foundries, and assembly lines responsible for the legendary V1710 piston engines and the T56 turboprops, was spun off into a distinct entity called the Allison Engine Company. This entity was isolated, packaged, and prepped for the auction block. The commercial gearbox division was retained by General Motors and officially named Allison Transmission. For the workers in Indianapolis, it was a profound psychological fracture. Families who had worked side by side in the Allison complex for generations were suddenly working for two different futures. The people casting and machining the turbine blades were now waiting to see which foreign or domestic conglomerate would buy their legacy. The people building heavy-duty gearboxes were told they were staying with Detroit. The engine company was being pushed out of the nest, but the name it left behind was about to learn how to survive on the American highway. The corporate surgery of 1992 and 1993 was only the beginning. The newly independent Allison Engine Company, stripped of General Motors' financial backing and forced to navigate a post-Cold War defense market, was standing on unstable ground. The market forces closing in around Indianapolis were unrelenting. This was a classic collision of Force 1, manufacturing and operating costs, and Force 6, corporate consolidation and brand survival. To survive in the global aerospace market, an independent engine company needs massive continuous capitalization. Developing a new turbine core requires billions of dollars in research, advanced testing facilities, and years of zero-revenue engineering. Allison had brilliant engineers, legendary factory floors, and a storied history in Indianapolis. What they lacked was the massive parent company umbrella of a global automotive or aerospace titan capable of absorbing multi-year development losses. By the mid-1990s, the writing was on the wall. The independent Allison Engine Company could not stand alone against global behemoths like Pratt & Whitney, General Electric, and Rolls-Royce. The company needed a buyer with deep pockets and a global commercial aviation footprint. That buyer turned out to be British. In March 1995, General Motors, which still held financial stakes and lingering interests in the transition, along with the independent leadership of Allison, finalized a deal to sell the Allison Engine Company to Rolls-Royce for $525 million. The reaction across Indianapolis and the broader American aerospace community was a mixture of resignation and quiet grief. The factory that had built the V-1710 engines for the P-38 Lightning, the J-33 turbojets for early jet fighters, and the T-56 turboprops for the C-130 Hercules was now owned by a British rival. The nameplate on the gates of Plant 8 changed. The engineers and machinists who walked the shop floor every morning found themselves answering to corporate offices in London. Yet the irony of the sale was written directly into the American landscape. While the aviation division was being packed up and shipped across the Atlantic to become Rolls-Royce Allison, the other half of the empire, the commercial transmission division that GM had kept back in 1992, was about to embark on a completely different kind of American triumph. The transmission division retained the Allison name for the highway. In 2001, when General Motors launched the groundbreaking Duramax V8 diesel engine in its heavy-duty pickup trucks, they bolted it directly to an Allison automatic transmission. Across America, at truck stops, on dusty ranch roads, and outside highway construction sites, truck owners began popping the hoods and checking the badges. They saw the name Allison stamped into the metal. The engine company was gone, sold to a foreign rival, but the name it left behind was hauling American freight. The orders slowed. The rule book changed. The parts got harder to find. The factory line moved. The sound faded. The badge remained. The world it powered was gone. The physical footprint of the Allison engine empire has not vanished from the American landscape. It has merely fractured into two distinct worlds that rarely speak to one another. In Indianapolis, Plant 8 still stands, though the names on the security badges changed long ago. Inside those massive, heavily reinforced walls, precision manufacturing continues under the ownership of Rolls-Royce. Workers still machine complex aerospace alloys, cast turbine components, and assemble high-bypass turbofans and turboshafts that keep modern military aircraft aloft. The engineering discipline born in a small racing shop on Main Street in 1915 still survives, buried deep within a global corporate aerospace giant. Yet for millions of Americans across the country, the name Allison has nothing to do with commercial aviation or the ghost of World War II fighter planes. Walk down the rows of an American truck stop parking lot at midnight. Listen to the heavy rhythmic idle of a Duramax diesel pickup truck hooked to a loaded livestock trailer, and you will see it. Stamped into the metal casing of the heavy-duty automatic transmission is a nameplate that connects a suburban driver directly to the legacy of Detroit's golden commercial era. While the aviation engine company was sold across the Atlantic, the transmission division kept the name anchored to the asphalt. The preservation community tells the rest of the story. At air museums from Dayton to Seattle, vintage aviation enthusiasts meticulously maintain and fly restored Lockheed P-38 Lightnings and P-40 Warhawks. When an Allison V-1710 V-12 is fired up on a sun-drenched tarmac, coughing white smoke before settling into a deep mechanical growl, it is not just an old engine making noise. It is a working relic of a time when American factories could pivot overnight to build 70,000 precision power plants for a global war. Across farm country and swap meets, old service manuals stained with grease, heavy iron parts bins, and faded dealership banners preserve the tangible memory of an industrial network that treated maintenance as a craft and durability as a baseline promise. The world that built Allison was defined by heavy iron, skilled machinists, guaranteed military supply chains, and corporate parents willing to finance decades of mechanical perfection. That world has passed. The defense budgets shrank, General Motors reorganized its survival around a different balance sheet, and global aerospace consolidated into a handful of multinational titans. America did not stop needing power. It simply stopped needing that kind of power. The piston thunder of the V-1710 has faded from the flight lines. The constant, high-pitched scream of the T-56 turboprop is slowly being replaced by quieter, software-managed turbofans. The old machine shops in Indianapolis have modernized into digital tolerance foundries, yet the iron still turns where it was left to work. Somewhere in an American highway rest stop, a heavy-duty pickup truck ticks quietly in the cold night air, the transmission housing stamped with a legendary name, waiting for a morning that no longer sounds the same. See you in the next one.